Hello guys, welcome to this class. In the last class we talked about matching and we dropped some formulas, and in this class we are going to be continuing from where we stopped. So what we are going to be explaining now is type of matching. The first type of matching I would like to drop here is called the lever. Number one, lever. The levers. Number two, we have the pulley. Number three, we talked about inclined plane. After inclined plane, number four, we'll talk about wheel and axle. Number five, after wheel and axle, we'll talk about screw. Screw jack. And after screw jack, we now, I think we are okay there. Yes, from screw jack. Okay, yeah, number five, screw jack. Okay, number six, we're not talking about gears or gears, anyone you call it, gears. So these are the 6 classes of machines that we will talk about. So first of all, let's go into it one after the other. Now note that each type of machines may have their own velocity ratio. What differs in those machines, lever, pulley, inclined plane, are their velocity ratios. Their velocity ratios have different formulas, and that's what we are going to be learning now. So let's start from the lever. What is a lever? A lever. Now, a lever, you can write it down. A lever is a simple machine that consists of a rigid rod or a stiff body. It consists of a rigid rod. A rigid rod means a strong rod. Are you getting it? A strong rod, like what I just draw. Pivoted about a stationary point. This rod will be pivoted around. This pivoted means fixed. There's a place that it is held, and that point is called what? The fulcrum. It's called the fulcrum. Now, an effort is applied at one point. It can be applied here to lift a load at this point, or this will be effort, or the effort will be applied here to lift a load around this point. Now, depending on the configuration of this fulcrum, this effort and this load give the class of lever. For example, if this fulcrum, are we getting it, is at the center, then we have load here, we have effort here. It is called a class 1 lever. Or if this effort, are you getting it? If this effort is at the center E, and we have load here L, and we have fulcrum here, that kind of lever is called class 3 lever. Why class 2 lever? If the effort is at this side, we have E here, we have load here, then we have fulcrum here, it's called class 2 lever. But don't worry, that's what we are going to be explaining now. Now, type of levers, classes of levers. The classes of levers. So I would like to explain class 1 level. Class 1 level. What are class 1 levels? What are class 1 levels? Class 1 levels is a type of lever, are you getting it? Where the fulcrum, also known as the pivot point, lies between the effort and the load. Where the fulcrum, are you getting it? Lies between what? The effort and the load. Where the fulcrum lies between the effort and the load. This type of lever is called a class 1 lever. This kind of lever is called what? A class 1 lever. The fulcrum lies between the effort and the load. That's just all. Now, examples of class 1 lever are, let's look at some examples of class 1 lever. Examples are your pliers. Now this is how your plier look. It's your plier. Are you getting it? Your pliers. Now note how your plier works. You have to apply effort at this handle, right? This handle, you will apply what? Effort, right? Then this point is called what? The pivot, or what? The fulcrum, or the fulcrum. Then this point is where you will put what? The load. So this point is called what? The load. So if you observe, we have the load here, L. We have what? The fulcrum at the center. Then we have what? The load, which is at the last point. So in this case now, this plier is what? An example of class 1 lever. Let's take your hammer for example. If I take a hammer, the hammer is like this, right? And that hammer, I apply it to remove a nail. This is a nail from the wall. This is the wall. What will happen? Your effort will be here, right? Effort. Then your load will be at this place. This is the load, the nail, your load. Then this is what? The fulcrum. This is the fulcrum. So if you observe, if we start from this load point, you will see that we get to the load first, right? Before getting to the what? Effort. Before getting to the fulcrum, before getting to the what? Effort. So it therefore means that this configuration is like load before effort, before what? Load before fulcrum, before what? Effort. Or if we also start from the other way around, if we start from here, we start from effort to the fulcrum to the load. So it is a class 1 lever because the fulcrum is between the effort and the load. So another example we also have here, is your scissors. Your scissors, these are what? Class 1 levers. Your scissors, the class 1 lever. Alright, it's a class 1 lever. This is how your scissors look like, right? And this is the load you put, this L. This is the fulcrum, and this is your handle where you put your hand, right? So this becomes what? The effort point. So if we start the configuration, we discover that we start from load before what? The fulcrum, before what? The effort. L, F, E. So when you have L, F, E, or E, F, L, that is load before effort, before fulcrum. Load before fulcrum before effort, or effort before fulcrum before load, it is what? A class 1 configuration. Alright, Other examples of class 1 configuration are crowbars. Crowbar is an example of class 1 configuration. We have seesaw. Seesaw is also an example of class 1 configuration. Now note, class 1 configuration, are you getting it? Class 1 configuration, note this very importantly, are direction changer. Class 1 configuration are direction changers. For example, let's take the scissors for example. If I look these scissors now, are you getting it? Remember that when I apply my force, when I want to cut maybe a cloth, there's a cloth or there's a piece of cloth material attached here, so I want to cut it with my scissors. If I apply my force here, this one will go down, right? This one will go down, then this one will go up, right? The force here will go up. Now when this one is coming down, look, when this one is coming down, what will happen here? This side being traced, the same rod will what? Here will go up. So what happens is that the machine has successfully changed my direction, because the initial point was for here, for this point to go down, then the output went up. Now what are these plates? This plate went up. Now the output, the input was up while the output was down. So in this case we call them what? Direction changers. Direction changers. Also they are called force and speed multipliers. Force and speed multipliers. Alright, now let's talk about class 2 lever. Class 2 lever. Class 2 lever. Class 2 levers. Now, what are class 2 levers? Class 2 levers are done in a way that the load is now in between the effort, are you getting it, and the fulcrum. The load is in between the effort and the fulcrum. So when we have the load in between effort and fulcrum, then we know that it is a class 2 lever. Or we can have fulcrum first before the load, before what? The effort. Anyway, but in this case, what is at the middle is what? The load. In this type of configuration, it is what? A class 2 lever. It is what? A class 2 lever. Examples of this class 2 lever. Examples of this class 2 lever is your wheelbarrow. Your wheelbarrow. Your wheelbarrow is an example of class 2 levers. Now this is how your wheelbarrow looks like, right? This is the effort. Now this is the tire. And if you put a load here, right, this place will be the load. Then this is where you carry your wheelbarrow. That place is the effort, and this place is what? The fulcrum, because this is where the body is fixed, right? Now when I start my movement, I will start from E, right, before I reach L, before I reach what? F. It therefore means that L is at the middle, while we have E here, and we have what? F here. So it becomes E, L, F. Load is at the middle. In this kind of configuration, it is what? A class 2 lever. Another example of class 2 lever is nutcracker. A nutcracker. For example, this is how your nutcracker look like. Almost the same structure like a plier, but this one is a bit different because the load is in between. So your nut will be here. For example, you want to crack something like a cashew nut, your nut will be here, or a groundnut. This is your nut, right? Then this point here will be the fulcrum. This is where the nut will be, the fixed point will be. It's called the fulcrum, F. Then now note that this nut is also known as the what? The load. This is what you want to use the machine to do. Then this side is what? The effort. The effort. in this kind of configuration, what happens? We have what? F first, right? Before we have what? Load, that's the note. Before we have what? Effort. You will discover that in the FLE, the load is in between. The load is what? In between. And this kind of configuration where the load is in between the fulcrum and the effort, it is called what? A class 2 lever. A class 2 lever. Are you getting it? Other examples of class 2 lever are your bottle opener. You can research them on your own. If we want to do more examples, we won't have time here, but let me just sketch how your bottle opener look like. Okay, so this is the bottle. All right. Now this is the bottle. The bottle is the load. Right? Sorry, the bottle is not the bottle, the cover, sorry. The cover is the fulcrum. That's where the machine is fixed. The cover is the fulcrum. Why this point is the load, right? This point is the load. Why this side is the effort. So there's a point here that is fixed. That is the fulcrum. While in between is the load. While this side is the effort. I know this is a bit technical, but I don't mean there is more of a picture. Like if there is a visual explanation, you can see it, but there's no problem about that. All right. So other examples are bottle openers, nut crackers, and that's all. Now note that class 2 multiplier are force multipliers, but they are also called force multipliers. They are what? Force multipliers. They are force multipliers. Alright, so since we are done with this, the next type of machine we will now look into is called the class 3 lever. The class 3 lever. Class 3 lever. What is the class 3 lever? In this case now, the effort is between the load and the fulcrum. The effort is between the load and the fulcrum. The effort is between the load and what? The fulcrum. Examples of this class 3 lever is the human hand. Now this is your hand, right? The human arm. It's also called the forearm. This is your hand. For example, you took something. Maybe you took a ball. Now this side is where you will feel the effort, right? This is the effort applied. Then this is the fixed point, the joint. This is the joint, the effort. This joint is called the fulcrum because it's the fixed point. We are considering this part now. This part is what we are considering. We are considering from this part to this part. Are you getting it? Now this load here, what you took is what? The load. So if you observe this configuration, the effort is between the load and what? The fulcrum. This is a third class lever. Another examples of third class lever are your tongues. Are you getting it? Your tongue, your forceps, and that's all. So thank you very much. Now let's talk about the velocity ratio of a first class lever. The velocity ratio of lever, sorry, not first class. I don't know, there's a lot of, I'm making a lot of vocal mistakes, but don't worry, let's continue. velocity ratios of first class levers. The velocity ratios of first class levers, are you getting it? It's very simple. It's just, remember, for example, if this is a lever, the velocity ratio of lever, sorry, not first class lever, the velocity ratio of a lever. It is a lever and this is the fulcrum, right? This is the fulcrum. The distance from here to this point, if this is where you apply the force, this is called effort, right? While this place will be what? The load. Now, the distance from this point to this point is what we call distance of effort, like the effort distance, all over the load, and this point is called what? The load distance, the L. So velocity ratio here now will be this distance. Are you getting it? V arrow will be this distance from here to this point, from here to this point. That is equal to dE all over this distance from here to this point. That will be what? dL. So just know the concept, not about dE or not about dL. Just know that it's from the fulcrum point to the effort point over the fulcrum point to the load point. Thank you very much for watching. In the next class, we'll talk about pulley, inclined plane, wheel, and axle. All will be in one video. So after that, we'll now talk about calculations involved in type of machines. Calculations involved in type of machine. Levers require much explanation. That was why the video was lengthy like this. Thank you very much. God bless you. Make sure you subscribe and share to your friends. Hello guys, welcome to this class. And in the last class we talked about classes of levers, and in that class we talked about class 1, class 2 and class 3 levers. First of all, we introduced the type of machines, and the first one was lever. And under lever, we know that we have what? Class 1 lever, right? Class 1 lever, class 2 lever, and what? Class 3 levers. And we said that in class 1 levers, what happens? The class 1 lever has what? The fulcrum F in between the load and what? And the effort. And we said that class 2 levers have what? The load in between the effort and the what? The fulcrum. And class 3 levers have what? Class 3 levers have the effort in between the fulcrum and the load. So this was what we did in our last class, right? Now in this class we are going to continue from type of machine. We have talked about lever. We are going to be talking about a pulley. We are going to talk about what? Pulley type of machine. So how does a pulley look like? A pulley consists of a system of rope and wheel. It consists of a system of rope and wheel, in which the wheel revolves. The wheel will revolve in a frame. So let me draw it. So the wheel is revolving around a fixed point, something like this. So for example, there's a rope here connected to something like this. So maybe this is the load, right? And this is your hand trying to draw the rope. Now there is something that you need to know, that the more you draw this rope downwards, what will happen is that this load will begin to go up, right? So if this one is coming down, this one is what? Going up. And what happens is that the effort it will take you to lift this load with your hand will be more greater than the effort it will require for you to draw this rope and lift the same load. So what happens is that this pulley system, are you getting it? The pulley system has helped you make work easier. So how do we calculate the velocity ratio of a pulley? Velocity ratio of a pulley. I told you that in machine that we don't have issue in type of machine. What we just need is the velocity ratio, because each machine has their own velocity ratio. The velocity ratio of a pulley is given by V arrow is equal to number, equals to number of pulley block, number of pulley blocks. So for example, let's do a quick review. Let me quickly sketch a machine, something like this. Now, what is the velocity ratio? What is the velocity ratio of this machine? What is the velocity ratio of this machine? Pause this video and answer. I know you didn't pause the video, but if you get this answer, you were right. The velocity ratio is 3. Why is it 3? Because the number of pulley blocks in the system is what? 3. That is 1, 2, 3. So when we are talking about pulley, we just need to count the number of pulley block in the system, and the number of pulley block in the system will give us what? The velocity ratio. Now let's talk about our next subtopic, which is what? Inclined plane. The inclined plane. Now, what is an inclined plane? What is an inclined plane in terms of machine? When we are talking about an inclined plane in terms of machine, we are talking about a slant height. Are you getting it? A slant height in which a load, this is the load, you can call it load, is being what? Rolled through. A load is being rolled through. This is the force F, or the effort. That was a mistake. Sorry, let me clean it. Alright, so let's continue. So in which what? A load L is being rolled what? Through. And I said that this point is what? The effort. Now let's consider how the inclined plane look like. Now, before we continue, you should understand that it is easier to roll this road through this point than to lift it from the ground to this point, right? Because when you roll it through this point, if it is a smooth surface, we discover that the work will be easy. So that is why we consider it as a machine. Now let us know the velocity ratio of an inclined plane. Velocity ratio of what? Inclined plane. Okay, now the velocity ratio of an inclined plane, let us draw a diagram of how an inclined plane look like. This is the slant height, this is the horizontal axis, and this is the vertical axis. Right? Now you should know that at this point there is an angle. There is an angle to the horizontal. Now remember that velocity ratio VR is what? Distance moved by effort, distance moved by effort, distance moved by effort, all over distance moved by what? Load. This is a short form, distance moved by effort over distance moved by what? Load. Now, what is the distance moved by effort here? Remember that in this triangle, this place is the opposite side of the triangle. This side is the hypotenuse side because it's the longest side, and you know this is the opposite because it's what? Directly opposite to the angle, right? And the remaining part become what? The adjacent, right? Now when I place my load here, when I'm pushing the load, remember that my effort will what? Go through the hypotenuse. True or false? My effort will be along the hypotenuse. So we can now replace this VR by saying VR is equal to, now the distance moved by the effort here is what? This side, right? That is what? The hypotenuse, also known as slant height, because slant height, the slant height, all over. Now, what is the distance moved by the load? Remember that even though we are pushing the load is moving from the ground to a point, right? Our aim is to go to this point. So imagine me pushing the load through this point, or carrying the load from the ground to this point. We still achieve the same aim, and that aim is to lift it up a height. So my distance moved by the effort is along the hypotenuse. Now the distance moved by the load is the height from the ground. Are we getting it? The distance moved by the load is what? The height from the ground. If it's here like this, it's here like this. So VRO will be what? Distance moved by effort over distance moved by load, which is, now distance moved by load is the opposite, which is also known as what? Vertical height. So we now prove it that VR is equal to slant height, is the slant height, right? And we know how we got slant height, which was the hypotenuse, right? HYP, the hypotenuse part, over the vertical height. So, and this vertical height is what? The opposite. We derive it in the last page. So velocity ratio for an inclined plane is number 1, slant height over vertical height. Write this down, it's very important. Slant height over vertical height. There is another formula I want you to understand here. This is formula 1. There's another formula we are going to be understanding from this side. Formula 2 is that under trigonometry there is something called SOHCAHTOA. SOHCAHTOA, and this is how it works. SOHCAHTOA, this is SOHCAHTOA. Now, first of all, for us to use this SOHCAHTOA, we have to look for the relationship between hypotenuse and opposite, and that is what? Hypotenuse and opposite, which is what? Sine, because sine carries OH. So S for sine, therefore means that we are going to say sine theta, are you getting it? Is equal to what? is equal to what? Opposite, which is what? The vertical height. We can say that sine theta is equal to opposite, right? And opposite is what? Opposite is vertical height all over hypotenuse, which is slant height. Now, sine theta is what? Vertical height over slant height. But we remember that in our first derivation, we know that velocity ratio is what? Slant height over vertical height. Now in this case now, sine theta is vertical height over slant height. What does it mean? It means that if I turn this formula upside down, I will have my normal velocity ratio, true or false? Because velocity ratio is the inverse of this formula. So if I turn this formula upside down, I will have my velocity ratio. That implies that sine theta, are you getting it? Is equal to what? 1 over V arrow. True or false? And if we make V arrow subject of formula, that is, we cross multiply, or if we do anything to just make V arrow, here the subject of formula, V arrow will be equal to 1 over sine theta. Are you getting it? So the two formulas here that we just need to note for an inclined plane is that number one, velocity ratio, V arrow, is equal to slant height all over vertical height. And number two, velocity ratio is equal to 1 over sine theta. This is for what? This is for inclined plane. Note this very down. And we know that the slant height is along this point and the vertical height is along this point. Why? This angle here is the theta. Now the next part we'll look onto in this course, the next type of machine we are going to be looking onto is called the screw or wrench. The screw and the wrench. Now, in considering the screw and wrench, what do we need to know? First of all, let us sketch how a wrench look like. If we sketch a wrench, and we have a screw or a bolt here that we need an effort, maybe your hand, to turn through. We need to know something that is very important. First of all, we know how the screw look like. This is the screw, right? This is how a screw will look like. And my drawing may not be perfect, but keep on doing it small. This little knot. Now you know that this knot, when I turn it, it will revolve, right? It will make a revolution, it will roll. And one revolution here, the distance of one revolution, for example, when this knot is rotating, when it rotates, is one pitch. Is called pitch. That is the distance here is called pitch. Why this point? So the distance the knot will roll is called pitch. Now remember that the distance from this knot, I getting it, the distance the boat will rotate is called what? 1 pitch. Now know that the distance from this hand to the spinal is arrow. Why is it arrow? Because it's turning a radius. You turn it through a circular path, right? For example, you turn it through a circular path. It is rotating. You are turning it through a circular path. So what happens is that velocity ratio for this now, V arrow is velocity ratio getting into V arrow will be equal to distance moved by effort. Now the distance moved by effort, to know the total distance moved by effort, is the circumference of the cycle this hand is moving, right? We are moving like this. It is forming a circular path. The knot is forming what? A circular path. It is circumference of the cycle, and the circumference of the cycle is what? 2 pi arrow, right? It is circumference of the cycle moved by this hand during rotation. So this hand, for it to tie the knot, it will move in a circular path. So the circumference of that cycle, according to basic mathematics, circumference of the cycle is what? 2 pi arrow, where arrow is the radius of the cycle. Now in this case, now we already have our arrow, so we just need to add what? 2 pi, true or false? So that's what? 2 that will be 2 pi arrow, right? That is the distance moved by the effort, your effort. What are the distance moved by the load? Remember that this boat is what we are turning, and this boat will move 1 pitch. 1 pitch is called P. It's also called, it's measure the distance, 1 pitch. So that will be what? Distance moved by load is 1 pitch. That is what? P. So we can say that the velocity ratio for this screw arrange is given by what? 2 pi arrow over P. 2 pi arrow over pitch. Just note it. If you don't understand the explanation well, you can comment below so I can explain it better in another video. Don't worry, with time we'll start doing animation, so explaining this with animation will be more better, or putting my screen on the camera all at the time. But for now, let's stick to the formula, which is 2 pi arrow. Arrow, are we getting it? Arrow is the radius of the wrench, is the distance of the wrench, is the length of the wrench. YP is the pitch of the boat. The pitch of the boat. So the pitch is always given, and the length of the wrench is always given. So when I give you the length of the wrench, you don't know that that is what? Arrow. Now, the next class of machine we'll talk about wheel and axle. Wheel and axle. Now, what do we mean by wheel and axle? So, wheel and axle, are we there? Wheel and axle consist. This wheel and axle consist of an axle. Are we getting it? Because they are together, we can't separate them. It consists of an axle that turns a wheel. Consists of an axle that turns what? A wheel. So the effort is applied. The effort is applied to one point. They are together. Are you getting it? Okay, now when, for example, let's imagine that this is a system used in drawing water from the well. So something like this. There's a rope here, and there is a bucket here. Like you see the thumbnail, there's a bucket here. Right? So what happens is that when I turn this wheel, just note one is turning the other. So for example, this is the axle. When I turn this axle, this wheel will be rotating, and when I turn this wheel, the axle will be rotating. So depending on the one I turn. So in this case now, let me turn the axle, because in fetching water, most times we turn the wheel, so it will rotate the axle, right? There are some cases where the axle is rotated, but all are together. So we'll derive it now. So when I turn this part now, it will rotate, right? And this one too, this small axle will rotate too. Now let us consider the rotation. And when the rotation is being on, the work is being done. Now note, when it is rotating, there is a distance move, and that distance is a circular distance. Now let's consider the radius of this wheel, which is what? Big arrow. And the radius of this axle, which is small arrow. Now velocity ratio V arrow is equal to distance moved by load. No, it's equal to distance moved by effort over distance moved by the load. Now the distance moved by the effort is the distance moved by this axle. It is the distance moved by this wheel, right? And the distance moved by this wheel is the circumference, which is what? 2 pi arrow. 2 pi big arrow. Now the distance moved by the load is this axle, which is what? 2 pi small arrow, which is the radius of this axle, because this one too will rotate and rotate along the small arrow. Now what happens here is that 2 pi cancel 2 pi, and all we have is to be V arrow. Are we getting it? V arrow is equal to, we now have what? Big arrow over small arrow. So we now say that for wheel and axle, the velocity ratio is given by what? Big arrow over small arrow. Make sure you write this down, it's very important. Big arrow, where big arrow is the radius of the wheel, over small arrow, where small arrow is the radius of the axle. So it can be given to you in your exam. Now the next part we talk about is gas, the gas system, or gas, anyone you call it, gas or gas. This system consists of a mechanized machine where we have teeth. The first one has teeth, but both of them has teeth, right? Both of them has teeth. Now in this teeth gas, one is rotating and the other one is rotating by the rotation of the first one. So the first one, where the energy is coming from, is called the driver gas. It's called the driver gas, and the second one is called the driven gas. It's called the driven gas. Why? Because when this driver gas is rotating, since this one is connected to it, this one too will also what? Rotate. So this is the driver and this is driven. Now the number of teeth here now, is at those points. These are the number of teeth: 2, 3, 4. If we continue to count, we begin to get it clearly. These are the number of teeth for the driver jars, and these are the number of teeth for what the grieving jars. So what happens is that velocity ratio is distance moved by effort over distance moved by load. Now for this velocity ratio for gas is given by number of driver teeth. Are you getting it? Number of driver teeth over number of driven teeth. What does it mean? In this case now, since this is the driver teeth, it means that the total number of teeth here, if we count those teeth, the total number 1, 2, 3, the total number of teeth here all over the total number of teeth here. So we say that velocity ratio, are we getting it, for gas V arrow is equal to what? Number of driver teeth. They can give you the number as 5, anyone, but it will be in number. Driver teeth all over number of driven teeth. Wow. So since we are done now in explaining all types of machines and their velocity ratios, let's now talk about a complex machine. In less than 5 seconds will be through. A complex machine is a combination of many types of simple machines. Very simple. That is the definition. A complex machine consists of the coming together of different simpler machines. So we can make a complex machine by adding different simple machines. We can add a pulley, and a gear. After a gear system, we add inclined plane. Just adding different type of machines, different type of simple machines gives you a complex machine. So thank you very much for following this class. In the next class, we are going to be solving problems, exam problems that are related to this course, so that we'll be able to know how those things work very well. Make sure you like and subscribe, and also share to your friends. God bless you. Okay, hello guys, welcome to this class. And in the last class we talked about machine, and when we talk about machine, we said that a machine is a device which enables a force at a point to overcome a load at another point, right? Then working on other points, the overall thing is that it makes the work easier. So we defined some terms about machine, but we said mechanical advantage, MA, is how much the machine has been able to help your force, right? So is the ratio of load to effort, right? We said that velocity ratio is the ratio of distance moved by load. Are we getting it? Distance moved by load. Distance moved by load. Distance moved by load. All over distance moved by effort. No, sorry. Is distance moved by effort? Distance moved by effort. All over distance moved by load, right? So we say that velocity ratio is distance moved by effort over distance moved by load. And we now said that efficiency, EF, is the ratio of mechanical advantage to velocity ratio times what? 100. And also we said that mechanical advantage is work done by the load over work done by effort times 100, right? And we gave some kind of things. Okay, so we are going to be using those formulas in solving problems, right? We'll be using those formulas to solve problems, and after we solve those problems, the next class will be on types of machine. right? So we just solve simple question like 2 or 3. Then on that type of machine, that is where after explaining that, we now round it up with the final problem. All right, so we go to type of machine. No, sorry, we go to our first problem here. It says a simple machine has an effort. You know, in physics, when you are reading the question, you write it out, right? A simple machine has an effort of 2 newtons. So we say that E is equal to what? 2 newtons. Are we getting it? Over a distance of 5 meters. So we say that the distance here, distance equal to what? 5 meters. Are we getting it? It's used to push a load of 8 newtons. So L here is what? 8 newtons over a distance. Now the distance moved by this load is what? The distance of load is equal to what? 1 meter. Now this side is distance of what? Effort. Are we getting it? Okay. Now let's say A, find the velocity ratio of the machine. A, velocity ratio. We know that velocity ratio is equal to what? Distance moved by effort over distance moved by load, right? Now distance moved by effort from here, first of all write it down. Velocity ratio is distance moved by effort all over what? Distance by load. Distance moved by load, right? So V arrow will now be distance moved by effort from the question is what? 5 meters. So that will be 5 meters will be on top, right? Over distance moved by load. And distance moved by load here is what? 1 meter, right? So 5 over 1 is the same thing as what? 5. So the velocity ratio of the machine is what? Is 5. Now what is the unit of velocity ratio? The velocity ratio doesn't have unit because distance moved by effort and distance moved by load, distance and distance are the same unit. So when the, okay, let us say this is 5 meter, 5m, 1m, right? M cancel m, so there will not be unit here, right? Okay, very simple. Now the next question here is the mechanical advantage of the machine, FA. We know that FA, are we getting it? FA is equal to what? Effort. Oh, sorry, MA is equal to load over effort, right? That will be MA is equal to load over effort, right? Now the load here is what? 8 newton, and the effort here is what? 2 newton. So 8 over 2 is the same thing as what? 4. So the mechanical advantage of the machine is 4. Also again, mechanical advantage have no unit. Why? Because this is 8 newton and this is 2 newton. What happened? Newton and newton will cancel out, right? Newton and newton cancel out. There will be no unit here, so it will be 4. Now the next question here is what is the efficiency of the machine? And I say you should remember efficiency. Remember the name marvelous. MA over V arrow, right? Times what? 100. Now we have calculated the mechanical advantage to be 4. So that will be 4. And the velocity ratio to be what? To be 5, right? So MA is 4. Okay, we are following it. And V arrow is 5, right? Now times 100. So 5 going to here, 1. 5 going to 100 is 20, right? So 20 times 4. 20 times 4 is equal to what? 80. So the efficiency of the machine is 80%, right? So simple as that, very easy. Now let us go to our number 2 question. It says an effort of 300 newton is applied to a machine to lift a load of 1500. The machine has a velocity ratio of 20. Calculate A, the mechanical advantage, and number 2, the efficiency of the machine. First of all, what you should understand here is that you are giving effort. So when you are giving effort, you are giving E to be equal to 300, right? 300 newton. It's applied to a machine to lift a load. So the load here, are we getting it? Is 1500. Any complaint? No. Okay, the machine has a velocity ratio of 20. So V arrow here is what? 20, right? Now they are asking you to calculate the mechanical advantage.
Now, when they ask you to do something like this, what do? First of all, you recall that mechanical advantage, you get the formula of what they are asking you to calculate for. Now, what's mechanical advantage? Mechanical advantage, MA, is equal to what? Load over effort, right? Now, we have given load as 1,500, and we are giving effort as 300. So we just substitute to this equation. MA will be equal to 1,500 over, sorry, my pen is this, over what? Over 300, right? So 0 cancel 0, 3 go into year 1, 3 go into year 5. So mechanical advantage here is 5, right? Now, what of the efficiency? The efficiency will now be, we remember the name marvelous, efficiency equal to marvelous, so that will be MA over VR times 100, right? So we have calculated MA to be what? 5, so that efficiency will be equal to 5 over now the velocity ratio from the question is 20, right? Times 100. So 20 going to here 1, 20 going to here is 5, right? So 5 times 5 is 25. So the efficiency of the machine is 25%.